Bismillahirrahmanirrahim. Welcome to the new lecture of Discrete Mathematics. Today we are going to study about Introduction to Graph Theory. So what is graph theory? So a graph, let's see, we can say G. So a graph G is a collection of vertices which is denoted by V and edges which is denoted by E. Simple definition, collection of vertices and edges. So now what is vertices? So if you can see the dotted points, there, this is called, let's see, if you have this points, make it point. So this all is vertices. And what is edges? So when two vertices are come to be combined, this is called edges. Let's see, we are combining these two vertices. This is called edge, this is called edge. So combine it out at the end is one. So this is called edges. Okay, so we can say that a graph G equal to the combination of vertices and edges. So simple definition. So coming to some terminology. So the first terminology in a graph which we say that incidence. So what is incidence? So let's see this graph you can see. So this x incident to A and B. What means, let's say you have two vertices and both vertices are combining by x. So this x means this x is incident. Okay, it's simple. Then the second is adjacent. So you can see what is adjacent. Adjacent means a point, a vertex which can combine other vertices as well. So if you can see the B, so B is adjacent to C, B is adjacent to A, B is adjacent to E. So it means B are combining A, C and E. Okay, so B is not adjacent with D because B is not going to be aid or combining a D. Simple. So what is adjacent? Adjacent is, so B is adjacent to A, C and E. Or if you can say about A, so A is adjacent to only B. So it is only. If you can talk about E, so E adjacent to C, E adjacent to B. Okay, so the third is isolated. So isolated means which is not connected, a vertex which is not connected to any one of. So if you can see D is isolated because D is not connected to anyone. Okay, so this is some terminologies. So coming to undirected graph and directed graph. Undirected graph, what does it mean? Let's see, you have a edges, you have an edge and the vertex of AB. Okay, because edge is made by vertices. So when we have two vertices, it means we have one edge. Okay, just keep in mind, when we have two vertices, then we will have one edge. If one have three vertices, so we will have two. So it can be like can we say like vertices minus one, like something like that. Okay, so let's see this one about undirected graph. Undirected graph means you cannot mention the direction from which direction you can go. So you can go A to B, you can go B to A. Okay, so it means A to B and B to A both are the same. Let's see if you can talk about this in undirected. So A to B is equal to B to A because you can go in any direction. You can go in this direction, you can go in this direction. It doesn't matter because it is undirected. If you studied about scalar and vectors, when a vector you already mentioned. So now if you can say like in general, it's like a scalar. You can go in any direction. Okay, because directional is. So then we have a directed graph, and directed graph again we have a vertices. So in this, if you can see, we can mention the direction date. So when we have a E prime is equal to AB, it means that AB in this direction. A is going towards B, B is not going towards A. Okay, so directed and indirect graph just have a bit of this differentiation. So if you can see here, then X and Y. So if X is like a C to A, X is C to A, and Y is A to C. So both are, and if you can see like we are going from A to B, so E prime A to B will not be equal to B to A because direction is matter here when we have a direction. So in this case it will not be equal. In this case it will be equal because it's undirected, but in this case it will not be equal. So one thing more, how we can know about the direction. So it's like you know about head to tail rule again. So again, not the same rule will be applied, but it's just a concept. Like A is the tail of A and head of B will combine, just like for a director. So an XY walk in a G is a sequence. What is walk now? Walk means you are moving from this point to any other point. So it means when you are moving, it means you are walking. So it means walking. So we are saying that XY means X. Let's see, this is your X point. Let's consider then this is your Y point. So you are moving from X to Y. So when you are moving from X to Y, then it will be the combination of vertices and edges. Okay, because you have a vertices and you will have a edges. So that's why we say that W, which is like a symbol of a walk is equal to the combination of edges and vertices which is moving from X to Y. It's just like a formula. So where edges is X minus 1, because I told you before, when we have a two vertices, then we have a one edge. So it's like a vertices minus 1. Okay, this is formula. So another thing is a closed walk occur when X is equal to Y. What does it mean? When you start from this one and move, then again come to this one, this is like a closed walk. Okay, so later on we will see it. So now coming to the like a walk of the object, like start from A to B or B to C, D and so on. So let's first of all we are saying that data object is going from, let's see, we are saying this is called E1. Okay, then E2, E3, 4, because edges you can mention the edges by E1, E2, E3, E4 and so on. So we can say that your E1, this is your E1, your E1 is equal to X. Okay, X is your start, then vertices V1. We are saying this both what is called V1. So it means that E1 is equal to X and V1 is vertices. If you are talking about 2, E2, let's see E2. So let's see E2, maybe this is your E2, let's consider it out. So E2 mean which is the combination of, because E2 what we are going, it was a V1, because vertices both, it was a combination like a vertices. So vertices V1, then vertices V2. Okay, and E2 already be here. And why we are not using X? Because X is your starting point and which is already been used. Then if you come to E3, so E3 is a combination of V1, V2, V3. Okay, so it's a simple method how you can find the edges or how you can find the walk, simply how to calculate the walk. Okay, so now coming to the walk, let's see, we are going from A to D. We are making a walk from A to D. So from A to D we have a multiple of a path, multiple of a way how we can go, how on which path we can walk. Okay, so let's see, first of all we can say from A to D we need to walk. So it can be like A is your vertex A E1. Okay, then if you can this way A E1 B E5 and at the end is D. So A1 B E5 and D, it's your walk. Simple. So just finding your, but one thing which is more important is we always try to find a shortest path. Okay, so later on we will also be see about this concept as well. If you can if you want to move for again from A to D with another path, so with another path again which path we can have A E1, then B E4 and D, it's again the same. Now come to the another path, again the same path for AD, which is be like you can see here, again we are moving from A to D. So A to D we can say A E1 B E2 C E3 and D, it's another path. Okay, so we will have a multiple of a path and always we just try to find out the shortest path, because when you are making a programming or when you are making some other kind of a structure, so you always try to find the shortest path, because you are going to reduce the delay between the vertices or edges, whatever you can say it about. So that's why finding a shortest path. Again the same one, we are going to again from A to D walk. Okay, A to D walk. So again we have a couple of, then A E1 and then A E1 Okay, AE1, BE1, again AE1, BE4, BE4 and D. Why? It's a repetition. Again, if you can say it's a repetition, which is not going to give any kind of advantages, but we can use it. Simply we can use it, but it's just a waste of our time. So the thing is, you can use the repetition of the edges and vertices, but just a wastage of time, so don't try to use it out. Okay, so another way how we can write about the work, so again A to D work, and we can say ABD, because ABD is you just mentioning the vertices because it is already known. So you can also be used at A to D work, which is ABD vertices. Simple. Okay, so just keep in mind how you can finding a path, how you can make a direction, how you can create a work, and so on. Okay, but always we keep in mind this formula x to y, which is the combination of blah blah. If you can see again A to D works from another way, so A, B, C, E, F, then again E, C, B and D. So you can also, but again it's a repetition. You can use it, but don't use it because it's just wastage of time. So now coming to the example of a close work. What is close work? Close work means starting and ending point will be the same. So how is it? Let's see, we want to come back to E. Let's see, E we have. So when you are moving anywhere, then come back to here, it's just like a close work. So let's see, E to E. So it means to start from E. So E to C, C to D, D to F, and F to E. So you can write it like this way as well. Another way, E to C and C to E, it's another path. And also you can find out A to C, C to D, B to C, and then C to E. Again you can use it out, but at the end how we can write, because you are coming back to E, so it means you just writing about E as well, because the initial and the final point is the same, so we can use the same vertex. So the vertex E is the same, and which is called trivial. Okay, so keeping that this point is called trivial, so keep in mind is always it will be used in different question in theory and theory as well. So you can scheme there will be right E trivial, so it means it's a closed path. So now coming to some more important concept, so which is called concept of a trial and concept of a circuit. So a trial is a walk with no repeated edges. Keep in mind whenever you are saying that this is a trial, so when this is a trial, it means there will be no repetition of a edges. It means if you are saying that you are moving from A to F, let's see, you are moving from A to F, so you are just coming from this point, this point, this point. Okay, there will be no, it means it's a trial. But if you are using that A to D, D to A, so when you give back to D to A, then you are using, it means you are using the edges, it means it's not a trial. So keep in mind. Okay, so the trail is kind of a work where you cannot use the repeated edges. As I told you before that we can use a repetition of our vertices. Okay, you can use, but don't, because it's just wastage of time. So that's why now the concept of a trail is here, because he's saying that in a trail, if you are using the trail walk, so in a trail walk you cannot use the repetition of a edges. Okay, so let's come to the example of A to F. I told you before we want A to F trial. If once you are going to use a trial word, so it means you are not going to use the repetition of edges. So A to F, so we have multiple of a path, so we are using like A to D, then D to B, then B to C, and C to F. So if you can use it, there is no repetition of any edge. So when there is no repetition of any edge, it means it's a trial. Okay, just keep in mind this concept because it will help you later on in your programming. So now coming to another example, let's see, we use ECED. Okay, if you can see ECED, like which is this one, EC, then back to CE, so EC and CE, so you just use the ones, so EC and then CE, then D. So it means what you are going to do, you are repeating the edge. So when you are repeating the edge of E6, E to C is E6 and C to E6. It means E6 is repeated. So when edge is repeated, so it's not a trail. Okay. Another one, if somebody said that A to A is a trail, A to A is a trail, how is it? Now say A to A is a trail, but in a case where you cannot repeat the edges. So A to A, we are using that A to D, then D to B, then B to A. It's fine, because here we just repeating a vertex and it doesn't matter in the sense of a trail. In a trail, we just say that you cannot repeat the edges. You can repeat the vertices, but you cannot repeat the edges. Another concept we are coming back, later on, that where we cannot repeat the vertices, but in a trail you just keep in mind just not repeat the edges. Okay, if you can say, if you can use for a to A trail, like A to D and D to A, again back, okay, just like a closed circuit, but A to D and D to A, but there is a repetition of edge of E2, which is twice, so it means it's not a trail in this case. But simple thing which is need to have in your mind, so don't repeat the edges for a trail concept. So again the same concept, A to A, which is a trail, start from this point, then come this one, then it's a closed trail as well, and it's a trail as well, because no repetition of what? No repetition of edges. If you can come like this one, come to this, then this, then this, then you come to this, then back to this and this one, so it will not be trail, because there is a repetition of E3. When E3 is repeat, it means it's not a trail. Okay, so now coming to the another concept, which is concept of a path. So a path is a walk with no repeated vertices. As I told you before, later on we will see. So now the instant we know about the vertices now. So a path is a walk with no repeated vertices. So it means here you cannot repeat the vertices. You can repeat the edges, but you cannot repeat the vertices. But you also cannot repeat the edges, because once you are repeating the edges, it means you are repeating the vertices. Okay. Okay. Coming to the example, then again we have a closed path. A closed path is a cycle. Again we are coming to, again it's just same like a circuit. So we are saying A to E. We need a walk from A to E. So A to E, we can move A to B, B to D, D to C, and C to E. So if you can see like this one, A to B, D, this and this. So if you can see, no repetition of any vertex. No repetition of any vertex. Then we can say A to A. For A to A, so we can move like A to B, B to C, and C to A. So A to A we use, but vertex is going to be repeat. But in this case we need a closed path. So for a closed path we can use it like that, but we cannot use like this one. If you I'm showing you now, if you can from for A to A, let's you can see like this one, that A to B, then B to C, then from C to B again, and you can move this again to A. So in this case it will not be a path, because the vertices are going to be changed. You can use this vertices because you need a closed path. Okay, for a closed path it can be possible, but not like that you are going to be repeat this vertex, you can repeat this vertex, then move this one. So you cannot do like that. So again then it's another path for from A to A, like you can come from A to B, then you can go B to C with no repetition of vertices, then C to E, then E to D, then you can move D to A. So it's a closed path as well, because the starting and the end point is the same without repetition of vertices. Okay, so this is also a closed path. This is a closed path, and also we can say a path is a walk with no repeated vertices. So keep in mind, and always differentiate a trail, and differentiation between the trail and the path. Okay, but keep in mind always, for a trail and for a path, just try to find out the shortest path, because as in a networking you study about OSPF, open system shortest path first. Okay, OSPF, so where we can see always try to find out the shortest path. If you are doing a network or programming, so there we can use the concept of a short path. So coming to a component of a graph, it's just like a graph is connected if there is an xy path. If there is an xy path, you know, x starting from x to y, and there will be a connection between the edges and vertices. There is an xy path for all xy belongs to a vertices. So how we can say, we denote the number of a component with the kg. So g is a graph and kg is a symbol for a representation of. So kg, what does it mean? It's showing that the number of a connected subgraph. Keep in mind, number of sub-connected graphs. So how many sub-connected graphs we have? Let's see. This is a different graph. This is a different one. This is a separate one. So it means we have a 3 subgraphs. So kg will be 3. Okay. Then again, if you can see the vertices which is connected here, the vertices which connected here, and this is isolated. Okay. So coming to the concept of contradiction, which is more important. Contradiction. So let W be a minimal walk from x to y. Let's start from x, it's a y. So between a x and y we have number of vertices and so on. Okay, so this is called xy path. So minimal walk mean you need to find always the shortest path. So you need to find a shortest path. So we have a 2 case in this. Case 1 with no repeated vertices. Let's see, this is your x and y, this is your x, and just have a other vertices. We are moving from x to y with this. Let's say this is A, this is B, this is C, and this is D. So no repeated vertices. We are moving from x to y. So A to B, B to C, and C, no repeated vertices. So we can also be moved from this, because we need to find the shortest path. So this is the shortest one. But what he's saying, he said no repeated vertices. So here we cannot repeat any vertice. Case 2, repeat vertices. So if in a contradiction you can repeat the vertices, you cannot be. But it's up to your point of view. It's up to you once you are doing a programming, when you are doing a networking. So in this case, maybe sometime we need a shortest path, which is just repetition of a vertices maybe. Okay, so case 2, which is repeated vertices. Repeated vertices mean, like, see, this is your point and we want to move from this point to this point. So we have a 2 different paths. What move from this, then this, then this. So then again we are passing the same. So when you are passing the same, it means we are repeating the vertices. But it can be possible, you can do that. But you can also be used like direct from this to this. You can also be moved from this to this. So we have a 2 different cases. In case 1 you cannot repeat the vertice. In the case 2 you can repeat the vertices. So it's just for your information how you can be make a walk for a x to y. So coming to the just like a summary, if you can say it, but which is most important, like we have a walk BD, not trial. Not trial mean repeat edges. When you are not repeat, so you can repeat your edges. So like from BD, this is B and this is your D. So it can be moved from B to E. Okay, then B to C, like B to E, then E to B, like this one, then back to this one, then this one, and then this one. So this is a walk, but you are repeating the edges. So this is a walk, but it's not a trial, because there is a repetition of edges. So second is trial BD. He's saying that trial. Now it's a trial. When you are saying it's a trial, so it means you cannot repeat the edges. Okay, so in this case, like BD, so move B to A to C. Okay, then C to B, C to B, then B to E, and E to D. Okay, so if you can see, no repetition of any edge. You can repeat the vertex, but you cannot repeat the edge. So it's a trail now. It's a trail, but it's not a path. Okay, just keep in mind, it's not a path, because in the path we cannot repeat the vertices. Okay, then coming to the path now, path BD. So path BD means B to C, like this way, B to C and C to D, because no repetition of any vertices. So simple, it's a path. Then coming to the circuit, circuit B to B, not a cycle. What does mean? Like circuit B to B, it's short from B, like B to A to C, C to D, then D to E, then E to G, G to F, F to E, then F to E, and then E to B. So this is your circuit, but not a cycle. Okay, so hope you guys get the concept behind the cycle and a circle, because in a cycle you know that there will be no repetition of any vertices, but in a circuit you cannot repeat the edges. Okay, so that's why, if you can see here, we cannot repeat the edges. Once we cannot repeat the edges, it means it's a circuit, but it's not a cycle, because we are repeating the vertices. Okay, that's why. So coming to the example, which is a bit complex. So he's saying that f of G, graph G, which is a combination of vertices and edges, where V is like V is the vertices and E is the edges, and G is a simple. It is a simple graph. Simple graph mean there will be a loop free. Loop free not be a loop like this one. Like this is a loop. Come back to this one. This is a loop. Okay, loop free, undirected, no multiple edges. So simple graph. Once I ask you, say draw the simple graph. So draw the simple graph and define. So you will define by, it will be loop free, it will be undirected, it will be no multiple edges. Okay, so this is called multiple edges. So multiple edges is not a simple. This is a simple one. Just simple loop free, direct. It's a loop free. It's a undirected. It's a no multiple edges. Okay. So prove that, he's saying that prove that 2e is greater 2e is less than or equal to v square minus v. So e is the edges and v is the vertices. Okay, so we need to be prove this factor now. It's a bit complex, but I'm telling you which is the simplest way how we can solve this. So one thing about a proof, like this is saying that how many edges we have? 2e. So 2e edges mean we have a 3 vertices, 1 2 3. So this is a vertices now. So once 2e, 2 mean we have a 3 vertices, and how can say about, so 2e mean how many vertices we have? A 3. And how many edges we have? 2. How many edges we have? 2. Just like this one. Okay, I just made it, but just like this one. So we can say that edges is greater or equal to, so this symbol we are using, this is called combination. So in next lecture we will study about a combination as well, combinator. Okay, so we say that it's a combination of vertices and it's a combination of edges. So how many edges we have? This one. So this is say that, so 3:2. How many vertices we have? 3 and 2. So coming to the proof now. So coming to the proof, like edges is greater or equal to the combination of vertices and edges. Edges was 2. So in a combination we have a formula, and the formula like we can use like factorial, like v into v minus 1 factorial divided by, so v into v minus 1 divided by 2 factorial. This is the formula, and 2 factorial, again 2 multiply 1 with the again 12 be 2. So we can use like age is greater as less or equal to v into v minus 1 divided by 2 factorial. 2 factorial is equal to 2. So this 2 is coming to this one, so 2 is less than or equal to v into v minus 1 and the combination, so it's your proof. So just it's about mathematics, it's just a bit complex, so you need to be thinking about, but this is like a combination of a vertex edges. So if you remember this thing, that edges is always one less than vertices, so hope this concept will help you in your question and you can be solve it out. So this is your lecture, so you guys can watch it out. If you have any questions, you can raise the in the comments, so I will try to answer it out. So and try to solve the book example as well. So thank you for your time. See you in next lecture.